We want to begin looking at solving our systems of equations. And a system of equations is simply several equations, and we're going to start out with two equations where the same ordered pair is a solution for both of them. It's where the same ordered pair makes both of the equations true. Now what ends up happening is if you have two equations, and these are going to be linear, so we have two lines, well, there's several possibilities. The two lines can cross in exactly one point. And so that point, that ordered pair, is a solution. It's a value that will make both of those equations true. And it would then be the solution to the equations. So that's what we would be looking for. Now, if our equations cross in exactly one point, then we say that these two systems are consistent. They're consistent. And because we had two equations, they're independent. So we have a system that's consistent and independent. Now, another possibility when you have two lines is that they will be parallel to each other. In this case, it's not exactly parallel, but they're going to be parallel to each other. In this case, there is no solution. There is no point that will make them true, both true. So we have no solution. And when we talk about the type of system, this is a system that is inconsistent. So you can have a system that is consistent and independent. It has one solution. You can have a system that's inconsistent. There are no solutions. Or another possibility is that you can have a system where you have a line. You can have another equation, but it graphs to be the same line. So those two lines are right on top of each other, which means this has an infinite number of solutions, because every point on the line will make both equations true. So you have an infinite number of solutions, and what we do is we say that this system is consistent and dependent. Not spelling that correctly. It's dependent. Because it depends upon at the point that you are as far as your solution goes. So these are the types of systems that we're going to have. Now, most of the time what we want is a system that crosses at one point, and those are fairly easy to solve. But we also want to be able to know if there is no solution when we have parallel lines or when they are the same line. So the first thing we're going to do is to take two equations and to decide if there is a solution. And so to do that, let's take the two equations, 2x minus 3y equals 4 equals negative 4, and 2x plus 4y is plus y. 2x plus y equals 4. Now what we would like to know is the point 1, 2 a solution? Well, to figure out if that point is a solution, what we have to do is to substitute that point into each equation. Now this is our x, this is our y, so we would have 2 times 1 minus 3 times 2, and we want to know, does that equal negative 4? Well, we would have 2 minus 6 equals negative 4, so yes, this is a solution. It makes well, we don't know if it's a solution yet. We know that it makes that one true. To know if it's a solution is we'll have to check and see if it makes the other one true. So we'll substitute in 2 times 1 plus 2. We want to know, does that equal 4? Well, we have 2 plus 2 equals 4. So yes, it does make both equations true. So it would be a solution. Now let's see if the point 7, 6 makes them both true. So we know they cross in at least one point, so let's see if they cross in more than one point so that these might actually be parallel lines. So we're going to substitute in, we would have 2 times 7 minus 3 times 6. And we want to know, does that equal negative 4? Well, we would have 14 minus 18, and that equals negative 4. So it makes that one true. If we go to our second equation, 2 times 7 plus 6, we want to know, does that equal 4? Well, we would have 14 plus 6, which is 20. So it makes one equation true, but it doesn't make both equations true. So no, that one would not be a solution. But to be able to tell, you simply substitute it in. And this is how you can go about checking your answers once we find it. Well, most of the time what we have are two equations and we want to find the point. We're not given a point to ask if it's a solution. We want to find that point. We're going to do this by several different methods. In this lesson, we're going to do it by substitution and by the addition method. So, and in some other lessons, we'll learn a few other methods of doing this. So by substitution, the idea behind substitution is you're going to take one equation, solve it for a variable, and then substitute that into the other equation. So if we have the two equations, 3x plus 2y equals 4, and 2x plus y equals 1. We want to find the value that would make both of these true. Well, we're going to take one of our equations and solve it for either x or y. It doesn't matter which. But it does make it much, much easier if you will find an equation that has a coefficient, a variable with a coefficient of 1. Well, this coefficient's 3, this one's 2, this one's 2, this one's 1. So I would take this equation and solve it for y. Well, if we solve it for y, we would subtract 2x, and we would get y is equal to 1 minus 2x. Now what we want to do is to take that value for y and substitute it into our other equation. So we'd have 3x plus 2, but instead of writing y, we're going to write 1 minus 2x equals 4. Now we have an equation with only one variable, and we know how to solve those. So 3x plus 2 minus 4x equals 4, using my distributive property. So I have 2 minus x equals 4. Subtracting 2 from both sides, I get negative x equals 2. Dividing both sides by negative 1, I get x equals negative 2. So that tells me what my x is. Now to find out what my y is, I'm going to take this value for x and substitute it back into this equation. So y is equal to 1 minus 2 times negative 2, which would be 1 plus 4, or 5. So the point negative 2, 5 would make both of our equations true. If we check, 3 times negative 2 is negative 6, plus 10 would be 4. 2 times negative 2 is negative 4, plus 5 would be 1. So that would make both of those true. Since we had exactly one answer that would make them true, then this would be a system that's consistent and independent. All right, let's look at another one that we'll do by substitution. 3x minus 4y equals x minus y plus 4. And 2x plus 6y equals 5y minus 4. Well, we're going to have to do some work on these before we get started. We need all of our variables on one side, our numbers on the other. We want these in standard form. So we would need to subtract x, which would make that a 2x. Add y, which would make that a negative 3y, equals 4. Here we would need to subtract 5y. So we would have 2x plus y equals negative 4. Now we can take this system and solve it. So what we want to do is we want to take this equation and solve it for y. It's the only equation that we have that had a coefficient of 1. Now, you don't have to solve it for the variable whose coefficient is 1, but it will be much, much easier if you do. So if I solve this for y, I would subtract 2x. Now, I'm going to take that value for y and substitute it into this equation. So I would have 2x minus 3 times negative 4 minus 2x equals 4. Removing my parentheses, I have plus 12 plus 6x equals 4. Combining my like terms, 8x plus 12 equals 4. Subtracting 12, 8x equals negative 8. Dividing by 8, x equals negative 1. Then to find out what my y is, I'll simply plug it into this equation. Y is equal to negative 4 minus 2 times negative 1, which is negative 4 plus 2, which would be negative 2. So my ordered pair would be negative 1, negative 2. And that would be the point that would make them both true. To check it, go back to your original equation and substitute it in. Okay, let's look at this one. Y is equal to 1/3 x plus 2/3, and y is equal to 5/7 x minus 2. Now this one looks a lot messier because it has those fractions. But one of the nice things that it has is both of these are already solved for y. So since they're both solved for y, we can set them equal to each other. So 1/3 x plus 2/3 equals 5/7 x minus 2. Now, back in one of our very first lessons, we had equations that had fractions, and we said that what we would want to do is to go through and multiply the whole equation, both sides of it, by the common denominator. Well, our common denominator for 3, 7, and 1 is 21. So let's just multiply each term by 21. All the things that you learn in one lesson carry over to the other lessons. So 3 goes into 21 7 times, so we would have 7x. 3 goes into 21 7 times, so 7 times 2 is 14. 7 goes into 21 3 times. 3 times 5 would give us 15x minus 42. 21 times 2. Now this equation will be a lot easier to solve. We want to get our variables on the same side, so we could subtract 7x from both sides. 15 minus 7x would be 8x. Then add 42 to both sides, so that would give us 56 equals 8x. Dividing both sides by 8, we get x equals 7. Okay, we want to know what y is, so we're going to substitute it back into an equation. Now we have a choice, and we can do it into either one, but since my x is 7, I would probably choose this one so that it will cancel. Y equals 5/7 times 7 minus 2. Well, my 7's cancel. I have 5 minus 2, which is 3. So y equals 3. So our point would be 3. our point would be, always want to put them in the form of an ordered pair where our x goes first. So our x was 7 and our y was 3. So if we checked, this would be 7/3 plus 2/3 would be 9/3, which reduces to 3. 5/7 times 7, that would be 5, minus 2 is 3. So it makes them true. Again, this would be a system that would be consistent and independent. We had one solution. Okay, we're going to look at one last one by substitution. So x equals 4y minus 8. 5x equals, or 5x minus 20y is equal to negative 40. Okay, we want to take an equation and solve it for a variable. We would like a variable whose coefficient's 1. Well, we have one right here, and it's already solved for x. So what we're going to do is take our other equation, where there's an x, we'll substitute in 4y minus 8, and minus 20y equals negative 40. So we have 20y minus 40 minus 20y equals negative 40. Well, 20y minus 20y is 0. Those subtract out, so we get negative 40 equals negative 40. Well, we're supposed to solve for a variable, and we don't have any variables. Our variables subtracted out here, and we were left with an expression, an equation with no variables, so we can't solve for it. Now, what we do is we look at these. This is a true statement. When it is a true statement, that means that you have an infinite number of solutions. What that means, this is the situation that we were looking at where the lines were right on top of each other. So we have an infinite number of solutions, and our system is consistent and dependent. Now, if our variables had dropped out like they just did and it had been a false statement, then that's when we would know that we had parallel lines and there was no solution. So that's how you know when these two situations occur. When the variables drop out and you're just left with a number equals a number, if it's a false statement, like 5 equals 4, well then they're parallel lines and it's inconsistent. There's no solution. When it's a true statement, there's going to be an infinite number of solutions and our system is consistent and dependent. Now we need to know how to write that answer then, if that's the case. So we write our answer here in what we call set builder notation. We say our answer is the set of all xy's, of all the points xy, such that straight up and down line is how we write such that. And then we just write one of our equations because it's all the x's and y's, it's all the points that make one of those equations true. So if we graphed that equation, it's all the points on that line. And that's how we would write that answer. Right. Another method that we often use to solve our systems of equations is called the addition method, and sometimes you will hear it called the elimination method, because what you're trying to do is to eliminate a variable through addition. Well, the only way that you do that is if you have opposite coefficients. Negative 4 plus 4 is 0. We have our additive inverse property that says any number plus its opposite is equal to 0. So that's the idea we use in the addition method, is we want to have opposite coefficients so that when we add our equations together, we get 0 for that variable, and then we're only left with one variable. So let's take the system 4x plus 5y equals 3, and 2x minus 3y equals 7. Now, what we want to do first of all is look to see if we have opposite coefficients. Well, we don't. We have a 4 and a 2. We have a 5 and a -3. We do not have opposite coefficients. So what we want to do is to multiply one of our equations by a number so that we do have opposite coefficients. Sometimes we'll have to multiply both equations by a number. But in this case, if we multiplied this equation by -2, then we would have opposite coefficients here. And as long as we multiply the whole equation, we can multiply it by anything we want. So I'm going to leave this equation alone. And I'm going to multiply this whole equation by -2. Well, -2 times 2x is -4x. -2 times -3 is positive 6y. And -2 times 7 is -14. Now if I add these equations together, I get 0x, I get 11y, and I get -11. Now I have an equation with only one variable, and I know how to solve those. So I'll divide both sides by 11, and I get y is equal to -1. Now we want to find x. We have two ways of finding x. One way is just by substituting our value for y into either one of our equations and solving for x. The other way is to go back and take our systems and eliminate the other variable, where we can make this equation, we can multiply this equation by 3 and make that 15y, multiply this equation by 5 and make that -15y. So it's kind of up to you. Usually if my answer turned out to be an integer, I just substitute back in. So that's what I'm going to do, and it doesn't matter which equation. I'll take the first one, 4x plus 5 times -1 equals 3. So 4x minus 5 equals 3. Adding 5 to both sides, 4x equals 8, and then dividing by 4, x equals 2. So our solution would be 2, -1. This would be the point that would make both equations true. If we graphed our equations, this would be the point where they would cross. And we can look at a few equations that we actually can go through and look at the graphing. And graphing is another way we have of solving them. It's just not very accurate because they don't always cross at nice little integers like 2, -1. So let's look at another system. 2x equals 9 plus 3y, and 4y equals 8 minus 3x. Now, to do the addition method, one thing is your equations have to be in the same order, or they need to be in what we call standard form, where it's 2x plus, or it's x plus, it's ax plus by equals c. So we need it, our x and our y equals our constant. So to get this one in that form, we would need to subtract 3y. So we would have 2x minus 3y equals 9. Things have to be lined up. On this one, we would add 3x and put it first, plus 4y equals 8. So you always want to get them in that in the correct form, where your x's are lined up, your y's are lined up, and your constants are lined up. Now, in this case, I don't have opposite coefficients, and I can't get by with just multiplying one equation. I could make these 6 and -6, or I could make these 12. It's like looking for a common denominator. So since I'm going to have to do both equations, I'm going to get my y's to be opposites because I already have opposite signs. And that way I don't have to keep track of I've multiplied by a negative. So they would need to be 12. So I can multiply this top equation by 4. Well, 2 times 4 is 8x minus 12y equals 36. This one I would multiply by 3. If you can't think of the least common one, just multiply them by each other. So that would be 9x plus 12y equals 24. So when we add these together, we get 17x, my y's drop out, equals 60. And dividing both sides, I have 60/17. Well, that's a nice number, but I don't really want to substitute that back into any of my equations and try to solve for y. So here's where I'll do what I talked about earlier, is let's go through then and eliminate the x's. If we want to eliminate the x's, then we need a 6 and a -6. So we can multiply this top equation by 3. That makes that a +6, so I'm going to need this to be a -6, so I could multiply it by -2. So doing that, I would have 6x minus 9y equals 27. Make sure you do the whole equation. This would be -6x minus 8y equals -16. Now my x's drop out. I have -17y equals 11. Dividing both sides by -17, I get -11/17. So my solution, this would be a system that's consistent and independent. It's two lines that cross at one point, and that's the point where they cross. And you can see by graphing that would be very hard to read that number. So that's why we will use this method probably the most often. Okay, let's say we have as our system x over 6 minus y over 2 is equal to 1/3, and x plus 2y equals -3. Now, we don't want to have to deal with fractions, so we do what we talked about earlier. We're going to multiply this whole equation by the common denominator, which is 6. So we'll multiply each term by 6. Well, 2 goes into 6 3 times, so we would have 3x minus 2 goes into 6 3 times. Well, this was supposed to be a 6, x over 6. So that's going to not be a 3x. It was x over 6 times 6, so those cancel, and that gives me x. 2 goes into 6 3 times, so that would be 3y. 3 goes into 6 2 times, so that would be 2. So I have this as an equation, and then this is my other equation. And if it helps you, you can always write it again underneath here. Sometimes that helps you in figuring out which variable to eliminate. But here I'm probably going to eliminate the x's, and so I just need to make these this a -x. So I'm going to multiply this whole equation by -1. So I would have -x minus 2y equals +3. Well, my x's drop out. I get minus 5y equals 5. So y equals -1. To find out what x is, we can substitute it back into any of the equations we have. This one would probably be the easiest. So x plus 2 times -1 equals -3. X minus 2 equals -3. Adding 2 to both sides, x equals -1. So we have as our solution -1, -1. Now you can always check these by going back, and when you go back to check, you always go back to your original. So if we did that on this one, we'd have -1/6 minus -1/2. We want to know, does that equal 1/3? Well, we have -1/6 plus 1/2, getting us a common denominator, which would be 6. 1/2 is 3/6. So -1/6 plus 3/6 is 2/6, which reduces to 1/3. So that would check out. The other one, we'd have -1 minus 2 is -3. So it checks out in both of them. All right, let's look at one last one where we'll solve by the addition method. And we're going to do this more in the next lesson with 3 equations and 3 variables. So let's take this one. We have 5x minus 2y equals 4, negative 10x plus 4y equals 7. Okay, we don't have opposite coefficients, but we could get our y's to be opposites by multiplying this top equation by 4, or by 2, by making it 4. So let's multiply that top equation by 2. So we would get 10x minus 4y equals 8, negative 10x plus 4y equals 7. Adding them together, our x's drop out and our y's drop out. So we have left on this side is 0 equals 15. Well, here again we have a system where all the variables dropped out, but in this case we have a false statement. 0 does not equal 15. So since this is not true, then there is no solution. This would be a case of having parallel lines that never crossed. There's no solution. And this system would be inconsistent, is what the type of solution that we would call this. All right, what we want to do then is look at a few applications of these types of systems where we would go through and find some values. So let's look at this problem. The sum of two numbers is 2. If one number is subtracted from the other, their difference is 8. Find the numbers. Now, you may have worked these types of problems when you tried to deal with just one variable, but it's a lot easier when you can work with 2 separate variables. So we're going to let x be one number and y be the other, if you want to put it that way. It's the other number. So we have 2 numbers. Now the sum means that you're adding. So that would give us the system, or the equation, x plus y is 2. The sum of 2 numbers is 2. If one number is subtracted from the other, now we didn't designate one number bigger than the other, so it's not really going to matter which one we talk about. So if we say x minus y, it says their difference is 8. So here's our system. We want to solve it. Well, we already have opposite coefficients, so we could simply add these together. So 2x, our y's drop out, equals 10. So x equals 5. Then we could substitute into one of our equations. 5 plus y is 2. Subtracting 5, y is -3. So our other number would be -3. So we have 5 and -3. If we wanted to check it, and when I check it, I usually try to go back up to the written word. The sum of 2 numbers is 2. Well, 5 and -3 add up to be 2. If one number is subtracted from the other, so if 5 minus a -3 minus a negative's a plus, so that would be 8. Their difference is 8. So it does check out. So that's a case where you had to write the equation. All right, let's look at another one. This one's a little bit harder. It says the sum of 3 times a first number and twice a second number is 8. If the second number is subtracted from twice the first number, the result is 3. Find the numbers. Well, here we've designated that we're going to call 1 the first number, so let's let x be the first number, and y is the second number. Okay, and it says the sum. Now again, sum means to add. So the sum, that's going to be important. We're going to add of 3 times the first number. So 3x plus, so the sum of 3 times the first number and twice the second number. 2y, 3 times the first and twice the second is 8. So that gets us one equation. Then it says if the second number is subtracted from twice the first. So if we do twice the first minus the second number, the result is 3. These are kind of what we would call translation problems. Now, in this case, we don't have opposite coefficients. We have a 3 and a 2 and a 2 and a negative 1. So we're going to have to multiply one of our equations. If we multiply this second one by 2, then we'll have opposite coefficients. Or you could solve it by using the substitution method. So we get 7x, the y's drop out, equals 14, dividing x equals 2. Substituting back into either one of them, it doesn't matter. 3 times 2 plus 2y equals 8. So 6 plus 2y equals 8, subtracting 2y equals 2, so y equals 1. So our two numbers are 2 and 1. Again, we could check the sum of 3 times the first number, that would be 6, and twice the second would be 2. 6 plus 2 is 8. If 1 is subtracted from twice the first, that'd be 4 minus 1 is 3. So we found the numbers. Now, one other area where we use our systems quite a bit is when we get into some economics type problem, or when you get into business and you're trying to deal with what we call the break-even point, when we're dealing with cost and revenue. And we want to work with our problems, then we can deal with this. Before we look at that, we want to look at what we mean with our equations. We haven't really talked about the graphs so much. But if we have a system of equations here, now I've got 4 different equations up here, and you can look at them. We've got x plus 3y equals 12. This blue line is x minus 3y equals negative 6. And we've got x minus 3y equals 6 and x minus y equals 4. Now, if we wanted to find the two equations that had a solution of 3, 3, and we had a solution of 3, 3, then what we mean is we're looking for the two equations that cross at the point 3, 3. So these two, the x minus 3y equals negative 6, and x plus 3y equals 12 would have a solution of 3, 3. If we wanted the one that had a solution of 3, negative 1, well, there's the point 3, negative 1, so those two cross at 3, negative 1. Or we can, have our point here. But wherever our equations cross is the solutions for those. Now, we might want to look at these and see, are there any equations that never will cross? Well, it appears that this line, the blue line, and the black line would never cross, that they would be parallel lines. And we could check them, and if they had the same slope, which these are going to have the same slope, then they're parallel lines. So if you have parallel lines, then they're never going to cross. And you're going to know that you have parallel lines when you have two lines with the same slope but different y-intercepts. If they have the same slope and the same intercept, then they're going to be the same line. And so that would be the consistent and dependent. So this is what we're looking at. We're looking at where our lines cross. And we could actually graph our lines to find that point. But as we said earlier, when it turns out to be a fraction, then we can't read that from the graph too well. Okay, we also want to then look at what we call dealing with our revenue. We get our revenue. Revenue is money coming in. It's money you make. Well, most businesses make revenue by selling products. And so it's going to be the number of units that you sell times the price per unit. So our revenue would be equal to the selling price per unit times the number of units. And we'll let X be the number of units. Now, we also have cost. If you produce something, it costs you to produce it. So our cost function, which we'll call C of X, is equal to fixed costs. Now, fixed costs are things like rent on buildings. That's not going to change. It's always going to be the same. You've got whatever it costs you to your monthly payment, your mortgage. You may have to buy certain equipment. So you've got your fixed cost plus how much it costs you to produce each unit. So it's the production cost, or it's the cost of the unit per unit times the number of units that you produce. And usually when you're talking about cost per unit, you're talking about the materials that it takes to make that unit. Now, what usually banks want to know when you're wanting to start up a business is when you're going to break even. Because a lot of times when you first start a business, then your first things, it costs you more because you have all of the cost of buying things, and it's going to be a while before you start making money. So they want to know, well, when are you going to break even? And so they'll look at your revenue, which usually, the more units you produce or you sell, the more money you're going to make. And then they'll look at your cost. Well, you have your fixed cost and then your cost per unit. And usually the more units your cost, the less, that's point may not be going down. It doesn't always go down. Sometimes it's going up also, because the more units you produce, the more it's going to cost you. But they want to know this point. Where do you break even? Before that, your cost was higher than your revenue, so you were going in debt. After that point, your revenue is higher than your cost, so the difference in those two is your profit. And if the bank is going to loan you some money, well, they want to know, well, when are you going to start making a profit? And so this is called your break-even point. And your break-even point will occur when revenue equals cost. So let's look at a problem and see when we would find each of these. Okay, we have a manufacturer of calculators has a fixed cost of $300,000. In addition, it costs $30 to produce each calculator. They're sold for $80 a calculator. Okay, we want to find the cost function. Now, the cost function, which we'll call C of X, it was our fixed cost, which is $300,000, plus the cost per unit to produce. Well, it costs $30 per calculator. So 30, and we'll let X be the number of calculators. So that would be our cost function. Okay, we want to find the revenue function. That's how much we sell each calculator. That's our money we're going to make. Well, we're going to sell each calculator for $80. Okay, we want to figure up the break-even point. Well, that's when cost equals revenue. So that would be 300,000 plus 30x equals 80x. We want to know when those are equal. Well, if we subtract 30x, we have 50x. Then dividing both sides by 50, we get 6,000. Now, what this means is we would have to make and sell 6,000 calculators to break even. When we sold that 6,000 and first, When we sold 6,001 calculators, we would start making profits. That would be when we would start having a profit. Now, if we wanted to look at the graph of this, and this was kind of hard to graph because our units were so big. So what I did was I let each line represent $50,000. So this was $100,000, $200,000, $300,000. And then what I let each of our lines here, they represented 500 calculators. And so this was our calculators, this was our money. Over here, this was the money, and this was the number of calculators. So each line represented 500. So when I graphed this, this was my cost function. It cost me $300,000, and then it cost me $30 per calculator. So I went through and figured up some of the points as we went through. Uh, basically, looked at if I sold 1, 2, 3. I looked to see, well, 500 or 50,000 calculators, or $50,000 would be about 1,666 calculators would cost $50,000. And so 500, 1,000, 1,500, so about that. I just kind of estimated those as I went through. Then this would be my revenue function, and each one was representing 500, and I did my revenue function. And so if you look, right here is where they broke even. Well, if this is 500, then this would be 1,000, 2,000, 3,000, 4,000, 5,000, 6,000 calculators is what it would be. And then we could estimate, well, at that point, what the cost was. And so at that point, the money coming in equaled the money going out. So that would be 1, 2, 3, 4. So this would be $450,000, and it's about halfway between that, so about $475,000. We could actually have gone back and figured that up in our problem. If we're doing 6,000 calculators, then 6,000 times 80 would be $480,000. It would be costing us that to produce those, and we would have sold them for that amount of money, so we would have broken even. So these are some ways that we use systems of equations.